We're just going to take a few minutes today and do a quick problem session. I wanted to take one of the daily work problems that I had given my current students this semester and just look at a couple different ways to do it. This is a problem that relates to the properties of a factor group. And factor groups, at least for me when I was learning abstract algebra, were one of the trickiest ideas, intuitions for me to wrap my head around. And so what I want to do is take a very specific factor group question and look at how to do it in two different ways. A very straightforward way that uses the original definition of what a factor group is, and then a slightly more sophisticated way, the galaxy brain approach, that actually uses a characterization of factor groups using the first isomorphism theorem. So this is a problem that I'd assigned on a daily work assignment, and it looks like this. The problem says, suppose that I think about the group Z24. So this is the additive group mod 24. And within that group, I think about the subgroup generated by the element 8. So this is going to be the subgroup that consists of all the multiples of 8. So just 0, 8, and 16 are the elements in that subgroup. So the question asks, in the factor group of Z24 by H, what is the order of the element 14? And 14 here is understood to mean the equivalence class of 14 in the factor group. Or another way to think about it is it's the coset of H that contains the element 14, i.e. which is obtained by adding 14 to each of the elements of the subgroup H. So that's the question that's being asked. And before we even get started with the question, remember to convince yourself why this subgroup even has a factor group in the first place. This subgroup has a factor group only because this subgroup is normal subgroup of Z24. And it's a normal subgroup of Z24 because every subgroup of Z24 is normal because Z24 is an abelian group. Remember, anytime we're looking at an abelian group, every one of its subgroups is going to definitely be normal because there's no difference in an abelian group between adding on the left versus adding on the right. That's true of elements, and it's also therefore true of sets of elements inside of an abelian group. So since Z24 is abelian, we don't have to worry about whether the subgroup is normal. We know it automatically will be. So first of all, what is the straightforward way to answer this question? Just by using the definition of a factor group. How do I find the order of an element in a factor group? So first thing to remember about a factor group is that the identity element in a factor group is really, in disguise, the identity coset of the subgroup by which we are quotienting out. In this case, the subgroup is H, the multiples of 8, right? And so in the factor group, identity is just another way of saying belonging to H, right? So what that means is that when we talk about the order of an element, what we're really talking about, anytime we're talking about order, right, is how many times do I have to combine that element with itself using the operation of my group before the result comes back around to the identity. But now that we have a new understanding of what identity means, I guess I'll point using both a finger and an arrow here, that just means that we need to reframe the question about order. Instead of asking how many times do we have to add this thing to itself in order to get the identity, in the factor group where identity means belonging to H, really the question becomes how many times do I have to add this element to itself before the result is an element of H? How many times do I have to add 14 plus H to itself before the result lands me inside of H? Not lands me at the identity of Z24, but lands me at the identity of the factor group, which is the identity coset of H, in other words, which is the subgroup H itself. All right, so here's what this is going to look like. First of all, is this element itself the identity, 14 plus H? Well, based on what we know about cosets, we know the answer is no. 14 plus H is not going to equal the coset H, the subgroup H, unless 14 was already an element of H. And then in which case this would be true by closure, right? But since 14 doesn't belong to H, when I add 14 to every element of my subgroup H, I'm going to get some non-trivial coset of H. So we know for sure that in the factor group, the order of this element is not 1, because 14 plus H is not equal to the identity element. So we'll add it to itself once to test whether its order might be equal to 2. 14 plus H added to 14 plus H. Again, I can rearrange these 14s to get them next to one another because H is a normal subgroup, and so H plus 14 is the same as 14 plus H. So I can get the 14s together and make a 28. I can get the H's together and make H plus H. H plus H, remember, is a set. It's a set of all the possible sums of an element of H added with another element of H. But because H is a subgroup, it has the closure property, and therefore anytime I add two elements of H, my result is always going to be an element of H. So h plus h is the same as h as a set. Meanwhile, 28 in Z24 is the same as the element 4. So really what I have here when I add 14 plus h and 14 plus h is I have a coset which is most easily represented by 4 plus h. And again, since 4 doesn't belong to the subgroup h, we know that that coset is not equal to the original subgroup, and so the order of this element was not 2. We can check to see whether the order is 3, and it's not, because if I add 14 plus h one more time, I get 18 plus h. 18 does not belong to my original subgroup, and so 18 plus h is not the identity coset. But it's when I add the third time, 14 plus h added to 18 plus h, to look at the fourth power of my element. The fourth power of my element is represented by 32 plus h, but 32 in Z24 is congruent to 8. And now look at what happens. My subgroup h, I suppose I should have written this on the screen to begin with, but let me write it right now. My subgroup h has 3 elements in it. It consists of all the multiples of 8. And so the 3 elements are 0, 8, and 16. And once I add 8 one more time, I get 24, which brings me back around to 0. Okay. But this 8 plus h, because 8 already belongs to h, the closure property for subgroups says 8 plus h is equal to h itself. In other words, we have gotten back around to the identity element of the factor group by adding 14 plus h to itself a total of 4 times. And so the order of this element in the factor group is 4. So that is the straightforward, let's just use the definition of cosets and factor groups to do this. Right? We needed to know that h was a normal subgroup so that we could transpose this h and this 14 to get the 14s together to add them to make a 4. Right? But once we did that, we can just bang it out. And the most important insight there is to remember that being the identity element of the factor group means being an element of the subgroup by which we took the factor. And that is best illustrated, I think, in our more sophisticated approach to solving this problem. So let's think about how the first isomorphism theorem could have done the heavy lifting for us in this problem instead of having to grind out the calculation. So in this view, we're going to think about how to arrange the elements of Z24, all 24 of them, into a row by column pattern, using the first row of the table to be my subgroup, my normal subgroup H, and then using the other rows of it to be the non-trivial cosets of that subgroup. And then, because that original row, that original subgroup was normal, it means that the rows of this table are going to form elements of a group themselves. That group is the factor group. So we start just by writing the elements of H, 0, 8, and 16 in the first row of my table. And then the rest of the rows just become the non-trivial left cosets. Again, left and right don't matter here because this is a normal subgroup. And so one easy way of doing that is just by adding the numbers 1 through 7 to H. And I'm going to get these 7 non-trivial cosets. And I'll just fill in the rest of the numbers. For example, 3 plus H is going to be 3 plus 0, 3 plus 8, and 3 plus 16, and so forth. So all 24 of the elements in this additive group Z24 can fall into this nice row by column table. And why I like this table, of course, is that now it makes it easier to understand where the factor group is coming from. The factor group is going to have one element for each of the rows of this original table. So each of these rows that originally had 3 elements in Z24 is just getting squished down into a single element of the factor group. 0 plus H now becomes an element rather than a set. 1 plus H becomes an element instead of a set, and so on. And so I know, just based on this picture, I now have a nice visual for what the factor group Z24 mod H looks like. But of course the problem is, if we go back to what the question is asking, what's the order of the equivalence class of 14, the coset 14 plus H? Well, 14 plus H isn't written right now in my table. It doesn't look like it's one of the elements of this factor group. But we know better, because we know how cosets work. Why cosets work and how cosets work is that any one of their elements, any one of a coset's elements, is capable of representing all the others. And so however 6 behaves in this factor group, 14 is going to behave the same, 22 is going to behave the same, but they're probably going to behave differently than 2, 10, and 18, for example, right? So rather than thinking about this coset as the coset of 14, I can instead think about it as the coset of 6. Why do I get away with thinking about it as the coset of 6? Because the difference between 14 and 6 is 8, and 8 is an element of my subgroup, which means in the factor group, that 8 looks like the identity. And so when the difference between two things looks like the identity, that must mean that those two things are the same, right? Identity is kind of a proxy in group theory for not being able to tell the difference between two things, because when the identity acts, it does so transparently. We can't see it happen, right? And so the difference between 6 and 14 in this group is significant. We can tell there's a difference because their difference, 8, is not the identity. But from the perspective of the factor group, because 8 belonged to my coset, anything which belonged to this subgroup, anything which belonged to my subgroup, my normal subgroup, is going to be a difference between elements that we are no longer able to see. And so the difference between 14 and 6 is 8. That difference becomes invisible in the factor group because 8 becomes the same as 0. So the coset of 14 is the same as the coset of 6. And therefore the element 14 plus h is the same as the element 6 plus h in this factor group. So that's already sort of cuts our work down for us a little bit. Now we're asking the question, what's the order of 6 plus h in this factor group instead of 14 plus h? Hopefully that'll be a little bit easier to understand. But we still have to understand it, ideally without adding it to itself a bunch of times to figure out, right? So to do that, I want to understand more about what this group of order 8 actually is. Right? Up to isomorphism. Can we understand this group by translating it into our understanding of a group to which it's isomorphic, which we might understand better? Right? Can we replace this with an isomorphic group that we understand completely? And so what do we know about this group? Well, my original group was abelian. Z24, addition mod 24 is commutative, and so this is an abelian group. And therefore, any factor group of Z24 will also be abelian. So I have an abelian group of order 8. Based on what we know about the fundamental theorem of finite abelian groups, that thing that we sort of jumped ahead to learn, we know that there are 3 possibilities for what an abelian group of order 8 looks like. Right? Because 8 is 2 to the 3rd power, and there are 3 partitions of the number 3. There are 3 different options for this group. It could be a cyclic group, Z8. It could be a direct product of the cyclic groups Z4 with Z2. Or it could be what's called the elementary abelian group of order 8. Z2, direct product Z2, direct product Z2. So if we know the fundamental theorem of finite abelian groups, we can at least have some justification for saying whatever this factor group might happen to be, it's got to be one of these 3 things up to isomorphism. And these 3 things are all things that we can understand very well because we understand everything that there is to understand about cyclic groups, and we understand everything that we would need to know about how the elements of cyclic groups combine in a direct product. So for example, if my group turned out to be Z8, isomorphic to Z8, then I know that there would be an element of order 8, i.e. a generator. There would be an element of order 4, there would be an element of order 2, and there would be an element of order 1. If it were, on the other hand, Z4 direct product Z2, I know that there would no longer be an element of order 8 in my group. Same thing with this group, there would no longer be any element of order 4 in that group. So we have now some nice ways of understanding the kinds of evidence we would need to distinguish between these 3 different options. So let's see if we can figure out to which of these 3 options is this factor group isomorphic. And the way we can do that is by using the first isomorphism theorem. The first isomorphism theorem says that a factor group is always going to be isomorphic to the image of any homomorphism out of Z24 that uses this subgroup as its kernel. So any homomorphism out of Z24 that has a kernel equal to 0, 8, 16, that homomorphism's image will be isomorphic to the factor group by that normal subgroup. That's a mouthful. Let me fill in some of those details. So if I can find a homomorphism out of Z24 whose kernel is 0, 8, 16, exactly 0, 8, 16, no more, no less, if only those 3 things are getting sent to the identity and nothing else, then we are in good shape. So how might I do that? Well, one way that I might do that is just by constructing a homomorphism. This is a lot more detailed than you need to do with each one of these examples, but I just want to show it for the sake of showing it. Let me see. I don't want to have to write all 24 of these numbers, but I think I'm going to. 0, 1, 2, 3, 4, 5, 6, 7. Maybe I'll just write the first half of them. 9, 10, 11, 12, 13, dot, dot, dot. And then I'll write them again down here. So here's my trick. My trick is I'm going to come up with a homomorphism that definitely sends 0 to the identity, because homomorphisms have to send identity to identity. But I also need to send 8 to the identity. And when I send 1 to 1, I also need to send 9 to 1. When I send 2 to 2, I also need to send 10 to 2, and so on. In fact, what I'm doing here is I'm exactly sort of constructing this quotient map. And what the first isomorphism theorem is going to tell me is that these elements in this factor group are going to behave exactly like their representatives behave inside of Z24, with the caveat that when I get to a representative of 8, I end up back at 0. So in other words, I know for sure that this 1 is going to have the capacity to generate this group, because in Z24, 1 plus 1 is going to give me 2, plus 1 is 3, plus 1 is 4, plus 1 is 5, plus 1 is 6, plus 1 is 7, plus 1 again is going to bring me back around to the identity. So I know for sure that the order of 1 plus h in the factor group is going to be the same, or is going to be equal to 8. So that's how I know that this element, 1 plus h in the factor group, this element is going to have order 8. But my group itself already only has order 8. And so I know for sure now that my group has got to be the cyclic group of order 8. In other words, this factor group is isomorphic to Z8. And with all of that sophisticated machinery behind us, now that I've made this conclusion, that the factor group is isomorphic to Z8, now my new question is, what is the order of the element 6 in the cyclic group Z8? That's the kind of question we could have answered way back in Chapter 4 when we first learned about cyclic groups in order. Well, the order of 6 is the same as the order of the inverse of 6. Remember, that's true for any group in any element. Its order is the same as the order of its inverse. But in Z8, the inverse of 6 is 2. And with that lens on the element 6, it's the same as 2, and therefore the order is the same as 2, and therefore its order is going to be equal to the order of 2. How many times do I have to add 2 to itself before the result is a multiple of 8? 4 times. So this felt like, for me, this feels like a cognitively easier way to answer this problem using the more sophisticated tool work of the first isomorphism theorem. Notice that all we did, right, was we made the assertion that in order to find the order of this element, I should instead understand the algebraic structure of the whole factor group. That's the sort of the level of difficulty, where the level of difficulty comes from here. We first understand the algebraic properties of the whole group by using the first isomorphism theorem to, in this case, conclude that this group is isomorphic to the cyclic group Z8. Then, now that I know this group is isomorphic to Z8, I know how to find the order of an element, any element, in the group Z8. And the element we needed was the element 6. And we knew that's the element that we needed because the coset of 6 in this factor group is the same as the coset of 14, because the difference between 14 and 6 is a multiple of 8, in other words, a member of this subgroup. So there are two different perspectives on how to do a problem like this if you're asked to characterize the order of an element in a factor group. You can either take the sort of long way around the mountain and just grind out how many powers of this element before I get the identity, remembering that identity now means elements of the original subgroup H. When we did it that way, we were able to conclude that the order of this element was 4. But for the sake of the general theory and sophistication and understanding more about finite groups and where they come from, we can instead think about this factor group by understanding the entire algebraic structure of it, using the first isomorphism theorem, which says that the factor group is isomorphic to the image of this homomorphism. And the image of this homomorphism consists of the residues 0 through 7, and I observe that the element 1 has order 8. It can generate all the others, because 1 plus h is equal to 2, or 1 plus h added to itself is equal to 2. Added to 1 plus h again gives me 3, and so forth. So because I had an element of order 8, this group ends up being cyclic, so it's isomorphic to Z8, and therefore the order of this element is the same as the order of the element 6 in the cyclic group Z8, which we know to be 4. So I hope this was a helpful little diversion, a little unscheduled live stream for today. Feel free to leave questions, comments, either in Twitch if you're watching right now. You can leave them on the YouTube video or in our Slack channel if you're my current student after the fact. We're going to continue to talk about this process of understanding factor groups and what the first isomorphism theorem can do for us over the course of this week. So I look forward to doing that with you.